Hello everybody. So, I will start my lectures by summarizing what we did yesterday. So, the first point was that we defined current and we said current is a flow of electricity. Or electric charges if you like. The ability of a material to conduct electricity depends on the properties of the material. So, ability to conduct, in particular we are interested in what are known as conductors. We observed that conductors have what are known as free electrons. The free electrons belong to the material as a whole and are not bound to a particular atom or atoms. The point about the current electricity is, unlike in electrostatics where the field inside a conductor must be equal to 0, the electric field inside a conductor Having said this, we defined a quantity which is known as charge density. We did point out that electric current itself is not a vector, but we defined current density denoted by vector j, and we said in terms of this the current is given by j dot ds, where this is defined in such a way that the product j dot ds is positive for positive current flow. Primarily in conductors, the charge carriers, that is those which are responsible for conduction, are electrons. However, there are situations where we saw that ions can also conduct, particularly it happens in electrolytes. The point regarding the direction of the current is that though electrons are primarily responsible for flow of electricity, the direction of the current is primarily defined as the direction in which positive charges would flow if they were free to flow like the electrons. So, this is direction of the current. Towards the end of the last lecture, we defined what is known as a drift velocity. We said that drift velocity is the average velocity of the charge flow as a result of the presence of an electric field. So, we found that what happens in the presence of the electric field is these electrons which are free, they are able to, or they will accelerate, and in doing so they will go and collide with the static ions or atoms, And having done that, after collision they would emerge from these ions in arbitrary direction, though with similar speed with which they had collided, because the collision is nearly elastic. But however, since the direction is random, the average velocity of all the electrons taken together will turn out to be 0. But in the presence of an electric field, there is a general direction in which they move, and that is the average velocity direction. We also defined or obtained the relationship between the current density and the drift velocity by this relationship minus E n V d, where this minus sign is because we are talking about the drift velocity of electrons, and I have charge of an electron and the number density of the electrons. So this is the relationship between drift velocity and the current density. Here E is the magnitude of the electronic charge, which is 1.6 into 10 to minus 19 coulomb. Now I will illustrate these with a numerical example. So let me look at a particular problem. Suppose I have a sample of copper having a cross sectional area of 10 to the power minus 7 meter square, and suppose this carries a current of 1.5 amperes. We assume that each copper atom provides 1 electron to the free electron gas, and the density of copper atoms is rho, so not to confuse with n, is 9 into 10 to the power 3 kilogram per meter cube. Atomic mass of copper is 63.5 units. So our problem is to find out what is the drift velocity and the current density. The current density is fairly straightforward. The current density is simply the current I divided by the area. Current is given to be 1.5 amperes and area is 10 to the power minus 7. So therefore, this is 1.5 into 10 to the power 7 ampere per meter square. I had already obtained this relationship, J is equal to minus n E V. So in order to calculate the drift velocity, I need to obtain the electron density, the number density of electrons in the sample. Remember that what is given here is the mass density of the sample, which is 9 into 10 to the power 3 kg per meter cube. Now in doing so, I need to recollect a little bit of chemistry for you. So we know that 1 mole of copper has a mass of 63.5 grams, which is 63.5 into 10 to the power minus 3 kg. In addition, I know, and it has number which is known as the Avogadro's number, namely 6 into 10 to the power 23 number of atoms in 1 mole. With this data, I can immediately find out how many moles are there in 1 meter cube. So number of moles in 1 meter cube is 9 into 10 to the power 3 kg divided by 63.5 into 10 to the power minus 3. Well, I will calculate everything towards the end. So therefore, the number of atoms there, which will be the same as the number of electrons, is simply this number, 9 into 10 to the power 3 by 63.5 into 10 to the power minus 3 multiplied by the Avogadro's number, 6.2 into 10 to the power minus 10 to the power 23. And this, if you calculate, this works out to 8.5 into 10 to the power 28 per meter cube. And since I have said each atom has one electron contributing to the free electron gas, so therefore this is also the number of electrons n. So this is also identical to the n that we have talked about. So therefore my drift velocity magnitude is given by j divided by ne, and j was found to be equal to 1.5 10 to the power 7. N we have just now found out, 8.5 into 10 to the power 28 into electron charge, which is known to be 1.6 into 10 to the power minus 19. All these are in SI units, and if you calculate all this, this works out to a rather small number, 1.1 into 10 to the power minus 3 meter per second. That is equal to 1.1 millimeter per second. Now I would like to compare this number with other types of typical velocities that we have. So one of the things that you must know is that this is drift speed, not to be confused with the speed which the electrons have inside a conductor when it is able to move free. The drift speed is an average effect of all the electrons taken together. So let us look at what else we can compare this with. So average speed of electrons inside the material is fairly large, it is about 10 to the power 6 meter per second. That is the speed with which the electrons are moving inside the conductor and before they collide. But remember, the average of this over, because of their directions being random, is essentially equal to 0. There is another quantity which I would like to compare this with, is the thermal speed of copper atoms. Now this time I am talking about atoms. From kinetic theory, you know that the average kinetic energy, let me call it V thermal square, is by equipartition principle is 3 by 2 kT. So thermal velocity of the atoms is of the order of, ignoring the factor of 3 and things like that, kT over m, where k, occasionally written as kb, is Boltzmann constant. Which is 1.38 into 10 to the power minus 23 in SI unit, which has a little complicated dimensions, meter square kg per Siemens square degree. Now if you substitute this, what you get is, you can see it, this is 1.38 10 to the power minus 23. Let us take the room temperature to be 300 Kelvin, divided by the mass of copper atom, which we just now calculated to be 63.5 into 10 to the power minus 3, divided by the Avogadro's number, 6.2 into 10 to the power 23. And if you calculate all this, it works out to about 2 into 10 to the power minus 2 meter per second. So you notice that the drift speed of electrons is even smaller than this thing. And you see what happens if I am talking about electron mass here, because the mass here appears in the denominator. This number, that the thermal speed of electron, increases substantially, and you get this number, which is about 10 to the power 26 or so. So Vd is much less than the thermal speed of both electrons and of course even the ions. There is another characteristic speed, and that is the speed with which electric field gets established inside a conductor whenever you switch it on. Now that is essentially instantaneous, because the electric field speed gets established with a speed of the order of velocity of light. So therefore, drift speed that we have talked about is an extremely small number. I will come back to the way the drift speed arises with a little more detail later. But let me now talk about a large class of conductors. Now what is found is that a large class of conductors satisfy a rather simple relationship between the drift speed and the current density. And that law, which I will state in a slightly different way, is known as Ohm's law, and a very large class of conductor satisfies this. Now we know that between successive collisions, the electrons are accelerated by an electric field. Now so therefore, the drift speed is proportional to the electric field itself, and the current density, which is proportional. So let me say that the drift speed is proportional to the electric field, and I know that the current density by definition or by our derivation is proportional to the drift speed. That tells me that the current density J is proportional to the electric field, and we can write this as J is equal to a constant sigma times E. This is a vector relationship. Where the value of sigma is usually large for good conductors, and this is a property of the material. It is called conductivity. Now you can see what are the units of conductivity. It is the unit of J by E, and J is in ampere per meter square divided by volt per meter. So it has this unit, ampere per volt meter. This quantity is called a Siemen. So now normally this relationship J is equal to sigma E is written by writing the inverse relationship, namely E is equal to rho J, where clearly rho is nothing but 1 over sigma, and the unit of this is ohm meter. 1 ohm is same as 1 volt per ampere and is also equal to Siemen inverse. This rho, like sigma, is independent of electric field and it depends upon the properties of the material. Conductors are characterized by high values of sigma, or low values of rho. So, typical good conductors are, for instance, silver, which has a resistivity of 1.7 10 to the power minus 8. So, name of rho is resistivity. So, this is an ohm meter unit. Copper 1.7 10 to minus 8, aluminum 2.75 10 to minus 8, etc., etc. These are some good conductors. On the other end of the spectrum, there are good insulators. These are conductors. Insulators are those which do not readily conduct electricity. Typically, water is 2.5 into 10 to the power 5 ohm meter. Glass can have a value between 10 to the power 10 to 10 to the power 14. Between these two classes, there is a class of material which are known as semiconductors, about which you will be learning in detail in one of the or a few of the later lectures. Now, semiconductors are generally insulators at low temperatures, and as the temperature rises, their conductivity increases. In addition, the conductivity of semiconductors is substantially affected by impurities that might be present or impurities that might be put into, and typical resistivity of certain semiconductors. For example, if you look at resistivity at 0 degree of carbon in the form of graphite, it is of the order of 10 to the power minus 5 ohm meter. Germanium is 0.46 ohm meter, silicon 2300 ohm meter. So, we have talked about conductivity and resistivity, which are properties of the material, but let us now try to talk about a property which depends upon a particular sample. For example, let us talk about a sample which has a length of L and has an area A, cross sectional area A. We have seen that rho is equal to E by J. Now, let us look at, now I know that if I have a potential difference between the two ends, which is delta V, the electric field is delta V divided by L, and current density by definition is the current that is flowing through it divided by the area A. So, therefore, this quantity is if you take out the dimensional quantities there, so we will write it as delta V by A, delta V by I into area by length. Okay. Now, we define a quantity called resistance. This is quantity is called the resistance, and this resistance, which is the property of the sample, is given by rho times direct proportionality with L and inverse proportionality with the cross sectional area. So, this is characteristic of a sample, and of course, its material. So, you notice that resistance of a sample is directly proportional to its length and is inversely proportional to its cross sectional area. And this R, which we have defined as the applied potential difference divided by the current. If you plot this current as a function of delta V, you find this is essentially a straight line. Now, it turns out that a very large class of material follow this simple relationship, and in fact, most of the time, unless specifically stated, we assume that the conductors with which we work are ohmic material. So, let me sort of give you an illustration or an example to calculate the resistance of a sample. Let me take a block of copper. Suppose it has a dimension of 1 centimeter by 1 centimeter by 20 centimeter. So, let me try to draw it, not to scale obviously, because length should be 20 times as much. So, what I do is this. Now, one of the points that you have to realize is that the response of this to the electric field would depend upon which way you apply the potential difference. So, for example, supposing I decide to apply the potential difference between the long ends. So, this is my L, which is 20 centimeter. Then my resistance between these two ends, which we have said is rho L divided by the area. Rho is, I will take the data for copper that I had given you earlier, 1.3 into 10 to the power minus 8, and the length is 20 into 10 to the power minus 2 divided by the area, which is 1 centimeter by 1 centimeter. So, it is 10 to the power minus 4 meter square. And if you look at these numbers, so here I have got 2.6 into 10 to the power minus 5 ohms. Now, suppose instead you had applied the potential difference between the rectangular ends. Now, your numbers will change now, because what has happened is between rectangular ends, so resistance between rectangular ends. Now, I have the same number 1.3 10 to the power minus 8, which is property of a material. The length this time is just 1 centimeter, so that is 10 to the power minus 2, and the area is 20 centimeter by 1 centimeter, so it is 20 into 10 to the power minus 4. And if you calculate this, this is 0.65 into 10 to the power minus 7 ohms. The point to note is that while you can talk about resistivity of a sample, the resistance depends upon dimensions, and not only that, it depends upon, if you want to measure it, then it depends upon where exactly you have applied the potential difference. And so, resistance would vary depending upon which pair of points you have applied potential difference. Now, before I close this, let me bring out a similarity between charge flow and heat flow. Remember that right in the beginning, when I introduced the concept of an electric current, I had brought out a similarity with the flow of water in a tube. Now, you will realize that the similarity is lot more striking here, And let us again talk about a sample, and let us suppose that I have a sample of length delta x, and suppose across this I apply a potential difference of delta V. Then by definition of resistance of the sample, I know my current I is delta V divided by R, which is delta V divided by rho times its length delta x divided by the area. And if you write it, remembering that 1 over rho is nothing but sigma, so I get sigma A delta V by delta x. So notice that the current in this situation depends upon the gradient of the potential. Now, how does potential vary with distance? Now let us recollect. Actually speaking, if you wanted to write this as a proper relationship, so I will write dq by dt, which is my charge flow current, but I will put in a minus sigma A dV by dx, and that is because the positive charges move in the direction of decreasing potential. So since minus sign, because positive charges move in the direction of decreasing potential. Now let us look at what statement I can make about heat flow. If you recall your discussion when you discussed heat conductivity, you will realize the equation for heat transport was given by dq by dt is equal to minus kappa A, where this q in this case is actually the amount of heat instead of charge as we are discussing now. Kappa is known as thermal conductivity, A is of course the cross sectional area, and this is a temperature gradient. And this temperature gradient is required because heat flows from higher temperature to lower temperature. Now we immediately recognize there is a similarity. In fact, the similarity is not just accidental, and there is a reason for this similarity, and that is because transport of heat takes place by transport of electric charge. So typically a good conductor of electricity is also a good conductor of heat. Let me return back to the discussion of the drift velocity little more in detail. I would be looking at the microscopic aspect of it. But before that, let us remember that we said that Vd at most is a few millimeter per second. Now this does not imply that in order to start a current we will have to wait for long, because it is not as if the electrons are being literally moved from one end of a sample to the other. Just like in the case of a water flow, the electrons or the free electrons are already there, and if you switch on an electric field, the electric field, as we have seen, gets established with the speed of light, which in this scale is essentially instantaneous. And it is because of this that you do not actually have to wait when you press a switch in your home to light up something, because the electrons are already there right up to, let us suppose you are talking about a bulb, it is all there, and all that you have done is by switching on provide a pushing mechanism, as we did in case of water. However, there are transients, that is, the steadiness does not get established immediately. So, there is a bit of a time that it takes for the situation to become steady. The second point is that relationship between current density and the drift speed is minus NeV. Now, notice that we have said Vd is small, few millimeters. Electronic charge is also small. Electronic charge is 10 to the power minus 19. So, the reason why the current density is not that bad is because this is a large number, and we had calculated it some time back, and we found n is of the order of 10 to the power 28 per meter cube. So, this number, it more than compensates for the product of these two numbers, which is small. So, let me now look at why is Ohm's law reasonably good. And in order to do that, I will try to give you a microscopic picture of the situation that is happening there. So, let me get back to the beginning, and we said metals have free electrons, and these ones, they move like a gas inside the material. They do not belong to a particular atom or atoms. What we also said is that these electrons would collide with ions in the material. So, electrons, I have said already, the typical speed of electrons is of the order of 10 to the power 6 meter per second. So, electrons collide with ions and emerge with velocity in random direction, emerge from collision now. Because the direction in which they emerge from collision is random, if I define an average velocity of electrons inside a material, supposing there is a capital N number of electrons in it, and ith electron has a velocity Vi. So, this quantity is 0 on an average. That is because different electrons are moving in different directions, and randomly they are moving there. So, let us look at what happens if I now put in an electric field in it. So, we said in the presence of an electric field, the electrons would get accelerated. So, the way the thing works is this. So, in the presence of electric field, so electrons, which I will write for shorthand by E minus, get accelerated. But because the sample is full of atoms which are static, they collide. After collision, they emerge with velocity direction change. once again they would collide. So therefore this chain, acceleration, collision, acceleration, collision, so this goes on. Now what happens is this, so let me try to draw a typical picture. I will show the life of an electron over some time. Supposing my electron was at this point A, I will not show the location of an atom because it will clutter up the figure, but let us suppose the electron went there. So let me also show the direction of the electric field to be given by this. Supposing the electron was directed like that, and it goes there. So this is, I will just call it atom number 1. It collides there and would emerge from there with a velocity direction changed, though there is not much change in its magnitude of the velocity. And then of course it has a second collision, and let us suppose it now this time is directed like this. Undergoes a third collision, let us suppose this time it is, I am trying to draw essentially a random figure. So this is 3, this is 4. Then it, let us say, comes like this, this is 5, and let us say that once again, this is actually an arbitrary direction figure, so do not worry about any pattern in this. This is 6, and then finally it comes like this. So this is typical. I mean, you could draw any way you like. In this particular picture, I have shown you the electron goes through 6 collisions. Now what happens if there is an electric field? Now if there is an electric field, let us suppose my electron starts from A. Now remember that the electric field, right, is in this direction, and I have a negatively charged electron. So therefore the electron's velocity, because it has a velocity in the absence of electric field in this direction, but there is an electric field in this direction providing it an acceleration in that other direction. So therefore what will happen is that this electron would not quite follow this path, but what will happen is it will take a path which is fairly close to it and maybe go like this. Now this path, though I have shown it as a straight line, is actually slightly curved. Though over this length scale it would appear to be a straight line. The reason is that my direction of the acceleration due to the electric field and the direction of the velocity, they are not the same. So it is very similar to what happens to a projectile when you throw in an arbitrary direction with the gravity in a particular direction. So you know that the trajectory is a parabola. But only problem is that in this case my electron velocities are very large and the electric field that I apply is not that bad. But what is going to happen as a result is that this path is slightly towards the negative E direction because of the acceleration. Alright, then it undergoes a collision there, comes here, second atoms, and then it will go like that. So it will be roughly similar but slightly different. So notice that instead of arriving at this point, so let me call this original point where it arrived in the presence of absence of electric field as B, and this is going to arrive at B prime. So there is this slight drift in the direction of minus E, okay, and we have seen that the electron velocity is about 10 to the power 6 meter per second and drift speed is a few millimeter per second. So that is, the electron speed is greater than the drift speed by a very large factor. Now let us look at what exactly is the dynamics a little more quantitatively. So you notice that in the presence of an electric field, the acceleration of the electron, of course direction we know is opposite, is given by E over m. Mass of the electron is m. Now let us suppose the time between two successive collisions is tau. This is also known as relaxation time. That is where the electron is relaxing after a collision. Now suppose Vi was the velocity of the ith electron immediately after the last time it collided. Then in time t, which is less than tau, because in time tau on an average there would be another collision, but before the next collision occurs, the velocity after collision, let us call it by capital V. So this is given by the usual formula Vi minus E over m into t minus sign, because I am talking about an electron which must move in a direction opposite to the velocity of the electric field. So therefore, now remember I also mentioned that the average value of Vi, which is 1 over n times sum over I Vi, that is equal to 0. But if you look at this now, then the velocity close to a relaxation time would be Vi minus E tau over m. So therefore, my average drift speed is average of this, which is of course equal to 0 because this is random. But notice that this is not quite random, because it depends upon the direction of the electric field, which is given to be constant. So therefore, this is given by minus E tau over m. So therefore, the magnitude of the drift speed is given by E tau over m. Now this, so this actually connects the drift speed with parameters which depends upon the characteristic things like electric charge, mass, the strength of electric field applied, and a parameter which depends upon how frequently the collisions are taking place. So this is on dynamics of collision. But let us look at the relationship that we have, because we wanted to show why Ohm's law becomes valid. Recalling that my relationship between the current density J and the drift velocity was minus NeVd, that tells me that J is given by Ne square tau over m times E, and this has the same structure as equal to sigma times E. Thus, the expression for conductivity is Ne square tau over m. Ohm's law will be valid if sigma remains independent of E. So, this means Ohm's law's validity is the same as sigma being constant. Since in my expression here I have got n square over m, which depends upon the characteristic there. So, this implies tau is constant. By constant I mean independent of the electric field. Now, this is quite reasonable because we have seen that the electron velocity distribution, okay, this is independent of an electric field, and tau, which is the time between two successive collisions, would depend upon the electron velocity distribution and not on the electric field. And this is the microscopic reason why the Ohm's law remains reasonably valid. Now, I will conclude this with an example. Let me return back to the same example where I worked out the velocity of the drift velocity was shown to be equal to 1.1 into 10 to the power minus 3 meter per second. And this using this I want to calculate this quantity EEM by tau, so that my sigma, which is n square tau over m, or inverse relationship is resistivity. So, resistivity is m by n square tau. Remember, I have given you the data for rho, which we have said is 1.7 10 to minus 8. So, therefore, for copper 1.7 into 10 to minus 8, which is my resistivity, is m, which this is mass of the electron, so 9 into 10 to the power minus 31 kg, divided by n, which we calculated in that problem to be 8.5 into 10 to the power 28, into E square. E is 1.6 10 to the minus 19, so it is 2.56 into 10 to the power minus 38. And this times tau. So, take these numbers up and calculate this, and you will find this is of the order of 2.4 into 10 to the power minus 14 seconds. So, this is a fairly small time during which the electron remains free, and that is the typical relaxation time between two collisions. One occasionally defines a new quantity known as mean free path. Mean free path is the distance that a typical electron travels before undergoing another collision. Now, obviously, since time is tau, if I multiply this with typical velocity of the electron, so mean free path, which is frequently denoted by lambda or even L, is 2.4 10 to the power minus 14 times the velocity of the electron, which is 10 to the power 6. Let me take 1.6 into 10 to the power 6 meter per second, typical speed of electrons, and that happens to be about 40 nanometers. So, this is the distance that an electron would move without suffering another collision. So, let us quickly summarize what we did today. What we did is to look at little more deeply into how drift speeds arise in conductors. The other thing that we talked about is that the drift speed is small, but drift speed being independent, the drift speed being proportional to the current density, and the fact that relaxation time is independent of the electric field is the reason why Ohm's law turns out to be a reasonably good description of the phenomena that happens in case of conductors. We will continue with this in the next lecture and look at certain other parameters which are connected with conduction.